Snow piles against turf walls. Wind cuts across the Norwegian plateau at 30 degrees below zero. Inside the longhouse, a family sleeps on raised benches, wrapped in wool and fur. The fire in the central pit has died to embers. Yet the hall remains warm. This was not achieved by luck. They had an understanding, one that kept them alive through extreme cold. Between the years 793 and 1066, Scandinavian settlers built rectangular halls called langhus across Norway, Denmark, Iceland, and the edges of Greenland. These structures stretched anywhere from 15 to 75 meters in length, their size reflecting the wealth of the family inside. The longest excavated example, found at Huen in Denmark, measured 131 feet. But despite this variance in length, the width of these buildings remained remarkably consistent, ranging between 5 and 7 meters, regardless of who built them or their location. This was not arbitrary. The width determined thermal performance. A narrow structure meant less surface area through which heat could escape relative to the volume of air inside. It also ensured that warmth from a single central hearth could reach the outer walls evenly. Length could be adjusted for status and space, but width was fixed by the physics of heat retention. Viking builders had no formal training in thermodynamics, yet they standardized the one dimension that mattered most for survival. The longhouse functioned as a complete survival system. It was not simply a shelter. It was a machine designed to capture, store, and distribute heat through the coldest months of the year using only stone, earth, wood, and fire. The first challenge was the envelope. In a climate where temperatures could remain below freezing for months, the exterior walls had to resist the relentless leaching of warmth. Viking builders adapted their materials to the resources available. In Norway and Denmark, where forests provided ample timber, walls were constructed from planks or logs set on low stone footings. The wood was often treated by scorching, a controlled burning that carbonized the outer layer of each post. This made the timber harder and more resistant to rot, which was described in period accounts as the great enemy of wooden structures. Dampness accelerated decay, and scorched posts lasted longer in the wet conditions of Scandinavia. But in Iceland, the situation was different. Native birch grew sparsely and provided inferior framing timber compared to the oak and pine available on the mainland. Icelandic builders compensated by pivoting to turf. The resulting structure, called a torfbear, was formed using thick blocks of earth and sod to create both the walls and the roof covering. Beneath the turf sat a foundation of stacked stone, and within it, a light timber frame provided structural support. The turf walls were extremely thick. They functioned as natural thermal blankets. Turf is porous, filled with organic matter, and trapped air, which slows the conductive transfer of heat. But more importantly, the sheer mass of packed earth provided what engineers call thermal inertia, the resistance of a material to temperature change. A longhouse encased in tons of turf and sod would take hours to cool down, even as the external temperature plummeted. This thermal buffer was essential. Without it, the interior would have lost heat as quickly as it was generated. The roof added another layer of insulation. In timber-rich areas, wooden shingles were used. However, in Iceland, the roof was entirely covered in turf, creating an earthen berm that extended over the ridgeline. The entire structure resembled a low, organic mound rising from the landscape, with only the doorway and smoke hole visible from a distance. This massive earthen shell was the first line of defense, but it was only the beginning. Inside the longhouse, the floor was made of packed dirt, sometimes layered with ash to absorb moisture and control odors. Running down the center of the hall was an oblong trench, the Langelda, or central hearth. This was the heart of the structure, both literally and symbolically. The hearth was not lined with brick or metal. It was built using flat stones, arranged carefully beneath and around the fire pit. During the day, the fire burned steadily for cooking, light, and warmth. Wood was fed into the pit, and the flames directly heated the stones. Stone has high thermal mass. It absorbs heat slowly, but once heated, it holds that energy for a long time. As the fire burned throughout the day, the stones beneath it reached temperatures significantly higher than the ambient air. They became, in effect, a battery. At night, the fire was allowed to die down or was banked with ash to smolder gently. But the stones continued to radiate heat. This radiant warmth was steady and low level, sufficient to keep the interior livable without requiring constant fuel. Families could sleep through the night without tending the fire, and they would wake to a hall that was still warm. Archaeological evidence supports this. Hearthstones recovered from excavated longhouses are worn smooth and slightly depressed, showing centuries of repeated thermal stress. The stones absorbed and released energy night after night, year after year, until their surfaces polished under the heat. This system was efficient because it decoupled heat generation from heat delivery. The fire needed to burn intensely only during waking hours, when people were active and cooking. Overnight, the stored energy in the stones carried the household through the coldest hours without additional fuel consumption. In an environment where firewood could be scarce, especially in Iceland, this was the difference between survival and freezing. But stone alone could not solve the problem. The longhouse also had to manage airflow. There were no chimneys in Viking longhouses. Smoke escaped through an opening in the roof called the ljóri, a term that translates roughly to light hole or smoke hole. This opening was the only intentional vent in the structure, aside from occasional small gaps near the ridgeline called vindauga, literally wind eye, the origin of the modern English word window. When the fire burned, hot gases rose naturally. This is the stack effect. Warm air is less dense than cold air, so it ascends. In the longhouse, the high ceiling allowed the smoke to rise and collect in a dense layer just beneath the roof. This layer was thick, visible, and pungent. But it served a purpose. The smoke layer acted as insulation. It trapped the warmer, cleaner air below it, where people lived and worked. Heat rises, but if the rising heat is slowed by a dense layer of combustion gases, it cannot escape as quickly through the roof. The ljóri allowed just enough smoke to exit, preventing the hall from becoming unbreathable, but not so much that the structure lost warmth. This was controlled convection. The Vikings managed airflow with precision, utilizing the physical properties of hot and cold air to create thermal zones within the building. The lower zone, where the family slept, ate, and worked, remained relatively warm and breathable. The upper zone, filled with smoke, acted as a thermal blanket. But convection requires replacement air. As hot smoke exited through the ljóri, cold air had to enter somewhere to balance the pressure. If this cold air entered at wall level or through random cracks, it would create drafts that cut across the living space, making the interior uncomfortable. Archaeological evidence from some sites suggests a more sophisticated solution. Air vents underneath the hearth itself. If cold air were drawn in at the level of the fire pit, it would be immediately pulled into the flames and heated. This would feed the convective loop without introducing cold drafts into the occupied zones. The fire would receive the oxygen it needed, the smoke would rise and exit through the ljóri, and the replacement air would never chill the sleeping areas. This is advanced airflow management, achieved without the use of mechanical fans, ducts, or dampers. The system relied entirely on passive physics, on temperature differentials, buoyancy, and strategic vent placement. However, the longhouse was not just a matter of architecture. It was also biology. During the coldest months, livestock were often housed inside the structure. A section of the longhouse, called the Fyaos, was reserved for animals, including cattle, sheep, and goats. These animals generated constant metabolic heat. Their body temperatures ranged from 37 to 39 degrees Celsius, and in the confined space of the longhouse, this biological warmth supplemented the output of the central hearth. Animals are living radiators. They do not require fuel. Only feed and water are needed. Their heat is continuous, reliable, and free of charge. In the coldest hours of the night, when the fire had burned down and the stone hearth was releasing its last reserves of stored energy, the body heat of a dozen sheep or a pair of cattle could make the difference between a livable interior and a freezing one. This was biothermal integration. The Vikings were not simply cohabiting with their animals for convenience. They were incorporating animal metabolism into the thermal budget of the dwelling. Every source of heat mattered, and none was wasted. The interior layout reinforced this strategy. Along the inner walls of the longhouse ran raised wooden platforms called palar. These benches served multiple purposes, as seating, storage, and sleeping areas. Families slept on these elevated platforms, which were lined with straw and covered with animal skins for insulation. By sleeping above the floor, people avoided the coldest layer of air. Cold air is denser and sinks. The packed dirt floor of the longhouse was the coldest zone in the structure. The raised benches placed sleepers in the warmest available air, directly in line with the radiant heat from the central hearth and just below the insulating smoke layer. This was thermal zoning. The longhouse was not uniformly warm. It was warmest where people needed it to be. The floor could be cold, the roof space could be smoky, but the middle layer where families lived was optimized for comfort. Not all longhouses relied on the same strategies. In rare cases, environmental conditions allowed for exceptional adaptations. At Reykholt in Iceland, the farm of Snorri Sturluson, a 13th century chieftain and writer, archaeologists uncovered stone structures beneath the longhouse floor. These remains have been tentatively interpreted as components of an underground heating system fed by a nearby natural hot spring. If this interpretation is correct, it represents a form of radiant floor heating that utilizes geothermal energy instead of combustion. Iceland sits on a volcanic rift, and hot springs are abundant throughout the country. At Reykholt, builders appear to have channeled heated water through stone ducts beneath the floor, warming the interior from below. This would have provided consistent, smokeless heat without requiring constant fuel. This is an outlier, not a standard practice. But it demonstrates the adaptability of Viking engineering. When conventional resources were limited, builders explored alternatives. The thermal principles remained the same: capture heat, store it, distribute it slowly. But the methods varied depending on what the environment offered. The longhouse system worked. Families survived winters that would have killed them without these innovations. But survival came at a cost. In Denmark, a team of researchers conducted an experiment. Volunteers lived in reconstructed Viking longhouses for 13 weeks during winter, using open wood fires for heating and cooking. The researchers measured indoor air quality, focusing on two pollutants: carbon monoxide and fine particulate matter. The results were stark. Near the fireplace, carbon monoxide concentrations averaged 16 parts per million. Particulate matter, measured as PM2.5, particles small enough to penetrate deep into the lungs, averaged 3.4 milligrams per cubic meter. Personal exposure estimates, which account for movement throughout the hall, were lower but still significant. 6.9 parts per million for carbon monoxide and 0.41 milligrams per cubic meter for particulate matter. These concentrations were significantly higher than levels reported in modern studies of biomass-burning households. The longhouse design, optimized for heat retention, trapped not only warmth, but also combustion byproducts. Chronic exposure to these pollutants is associated with respiratory irritation, chronic bronchitis, and long-term lung damage. The Vikings had no choice. Minimal ventilation was necessary to maintain the insulating smoke layer and prevent rapid heat loss. But minimal ventilation also meant minimal dilution of smoke. The trade-off was unavoidable: endure the smoke or freeze. This was the survival paradox. The same system that kept families warm through sub-zero winters also exposed them to health risks that modern populations would find unacceptable. But in the context of a Scandinavian winter, where nighttime temperatures could kill within hours, the smoke was simply the price of staying alive. The longhouse was more than a thermal machine. It was also the center of social and ritual life. The hearth was where food was prepared, where tools were forged, and where stories were told. In larger longhouses, multiple hearth rooms sometimes existed. One hearth, near the entrance, was used for daily cooking. Another, set deeper in the structure, was reserved for more formal or ritual purposes. The fire was not just a source of warmth. It was the axis around which daily life revolved. The hearthstone itself held symbolic weight. It marked the boundary between the controlled space of the hall and the chaos of the natural world outside. Warmth, light, and human community existed on one side. Cold, darkness, and wilderness existed on the other. The fire represented order, continuity, and the survival of life. This symbolic importance extended across Viking culture. The hearth was passed down through generations, its stones worn smooth by centuries of use. When a family left a farmstead, the hearth often remained, a physical anchor to the land and the lineage. This pattern is not unique to the Vikings. Central hearths with thermal mass appear in cold climate cultures around the world, among Native American tribes, in medieval Europe, and in the yurts of Central Asia. The convergence is not coincidental. It reflects a universal solution to a universal problem: how to survive winter with limited fuel. Even today, in Iceland, the hearth retains cultural significance. The tradition of Jólabókaflóð, the Christmas book flood, centers around the ritual of gathering by the fire to read and share stories. The fire remains the place where community, warmth, and narrative intersect. The Vikings built their longhouses without blueprints, without formal education in physics or engineering. They worked through observation, iteration, and the accumulated knowledge of generations. They understood that heat rises, that stone retains warmth, that thick walls slow down heat loss, and that animals generate continuous body warmth. They encoded this understanding into every structure they built. The longhouse was not a single innovation. It was a synthesis of solutions. The turf envelope provided insulation and thermal inertia. The stone hearth converted combustion into stored radiant heat. The high ceiling and ljóri created controlled convection and smoke stratification. The raised sleeping platforms positioned families in the warmest air. The livestock provided biological heat. Each element reinforced the others. Remove any one, and the system would fail. This is a holistic design. The longhouse was not optimized for a single function. It was optimized for the entire range of conditions a family would face over the course of a year. In summer, the thick walls kept the interior cool, In winter, they retained warmth. The hearth provided heat, light, and a cooking surface. The raised platforms kept bedding dry. The smoke layer kept the upper zones warm while allowing the lower zones to remain breathable. The Vikings did not write manuals. They did not publish diagrams. But they passed down a system that worked, and that system spread across the North Atlantic. From Norway to Iceland to Greenland, the same basic principles emerged, adapted to local materials and conditions, yet always recognizable. The longhouse was a survival tool, as essential as a ship or a weapon. It was the technology that allowed human life to persist in one of the harshest climates on Earth. The longhouse fell out of use centuries ago. Modern Icelanders live in insulated homes with central heating, double-glazed windows, and mechanical ventilation. The turf houses that once dotted the landscape are now archaeological sites, protected and studied, but no longer inhabited. Yet the principles remain. Thermal mass is still used in passive solar design. Earth-sheltered homes still take advantage of the insulating properties of soil. Radiant heating systems still rely on the slow release of stored energy. The physics have not changed. What has changed is the scale of resources available. Modern builders have access to materials and technologies that the Vikings could not have imagined, including concrete, fiberglass insulation, and electric heat pumps. However, the core challenge remains the same: how to create a stable and livable interior in the face of an unstable and hostile exterior. The Vikings solved this problem with stone, turf, and fire. They built structures that understood the behavior of heat, the movement of air, and the limits of human endurance. They created spaces where families could survive not just one winter, but generation after generation of winters, in a landscape that offered little margin for error. This was not accidental. It was deliberate, informed by observation, and refined through experience. It was engineering in its most essential form, the application of knowledge to meet the demands of survival. The story of the longhouse is not a story of luxury or comfort. It is a story of sufficiency. The goal was not to create warmth indistinguishable from summer. The goal was to generate enough warmth to survive the night. The fire did not need to burn all day. The air did not need to be completely smoke-free. The structure did not need to be beautiful. It needed to work. And it did, across Scandinavia, across Iceland, across the settlements of Greenland. Families slept warm through winters that would have killed them in the open. They did so because someone, at some point, realized that stone holds heat. That turf slows heat loss. That smoke rises and can be managed. Animals generate warmth. That height matters when cold air sinks. These are not complex principles. They are observable, testable, and repeatable. But applying them consistently, in conditions where failure meant death, required not just knowledge, but discipline. It required building the same way, year after year, even when resources were limited. It required trusting the system, even on the coldest nights. The Vikings trusted the system because it worked. And it worked because it was designed not around theory, but around the realities of fire, stone, earth, and human need. Today we live in environments that are often insulated from the natural world. We adjust thermostats, not fires. We rely on power grids, not hearthstones. The distance between our survival and the technology that ensures it has grown so wide that we rarely think about it. But the longhouse forces us to think about it. It strips survival down to its essentials: shelter, heat, air, food. It shows what can be achieved with limited resources when the stakes are absolute. The longhouse is not a relic. It is a demonstration. It demonstrates that humans can engineer solutions to environmental extremes using only the resources provided by the landscape. It proves that sophisticated thermal management does not require advanced materials or complex machinery. It demonstrates that observation, iteration, and accumulated knowledge can produce systems as effective as any modern equivalent, provided the constraints are met. The Vikings did not conquer winter. They accommodated it. They built structures that accepted the reality of cold and designed around it. They did not try to eliminate smoke. They managed it. They did not try to eliminate cold air infiltration. They directed it. They did not try to heat the entire interior uniformly. They created thermal zones and placed themselves in the warmest one. This is an adaptive design. It does not fight the environment. It works within it. The Longhouse stands as a testament to what humans are capable of when survival depends on it. The system was not built by scholars or trained engineers. It was built by farmers, herders, and artisans who needed a place to sleep through winter. They observed how heat moved, how smoke behaved, and how materials insulated. They tested, adjusted, and refined their approach. And they arrived at a solution that kept their families alive. That solution was not written down. It was encoded in the dimensions of the structure, in the placement of the hearth, in the thickness of the walls. It was passed from builder to builder, from generation to generation, as a body of practical knowledge that required no explanation because it was visible in every hall. The Longhouse is a testament to human adaptability. It shows that intelligence is not measured by the complexity of the tools available, but by the effectiveness of the solutions produced. The Vikings had stone, wood, turf, and fire. They had observation, experience, and necessity. And from those elements, they built a machine that worked for centuries. We live in a different world now, but the principles remain. Heat must be captured, stored, and distributed. Cold must be resisted. Air must be managed. These are constants, as true today as they were 1,000 years ago. The Vikings understood this, and they built accordingly. Snow still falls on the ruins of longhouses across Scandinavia. The turf has eroded, the timber has rotted, the hearthstones have cooled. But the knowledge remains. The system remains. The proof remains. In the face of an environment that showed no mercy, humans built a structure that provided them with warmth and shelter. And that structure, in its simplicity and effectiveness, tells us something essential about survival, ingenuity, and the refusal to surrender to cold. The Longhouse worked, and that is enough.